Good morning, everyone. Today we are going to take up the next part of the geological work of river that deals with the transportation and deposition of sediments. We had discussed during the last lecture as to what is erosion, what were the different processes involved in erosion, like the sheet flow, solution, abrasion, attrition, cavitation, and the various landforms that were formed because of erosion. We had seen that V-shaped valleys are one of the very prominent landforms that are formed along with the rapids, waterfalls, potholes, etc. Now, whatever material that has been eroded by the above processes, it is transported downstream along with the moving water. Now, the sediments or the rocks which are broken down range in size from large boulders measuring tens of meters to very fine clay size sediments. Now, it is important to understand that the ability of the river to transport different size sediments depends upon the available energy of the river. Now, you can see here that these are the large size boulders measuring tens of meters in diameter. As a scale, you have a tree here, to these boulders which are few tens of centimeters in diameter. Now, the range from boulders, this also comes in the category of boulder, cobble, pebble, granule. We'll discuss what are the different sizes. And this is the different size of the sand. You have fine, medium to coarse sand. Then below this sand you have the silt and the clay sized particles. Now this is the table which gives the size of different sediments. So the boulder, if the size of the grain or the broken rock material is more than 2.56 millimeter, that comes under boulder. So you can imagine that even this small piece, it is a boulder which is say around 2 to 3 centimeters, and here you have got tens of meters. So the river has a capacity to erode such large fragments of rocks, and depending on the energy. So you have the boulder, cobble, pebble, granule, sand, silt and clay. The silt and clay together, they are also referred to as mud. Now whatever sediments are broken down, they are transported. Now the larger ones like the boulders and the pebbles, and the still heavier ones like the sand and the gravel, which the size we saw in the last slide, they are categorized as the bed load. That means these size sediments, pebbles, cobbles, gravel and sand, they move almost all along the floor of the river channel. So they are moving along the bed of the river, and the heavier ones like the boulders and the pebbles, they move by rolling, sliding. They are just, and some smaller ones, they move by saltation. That means they get picked up, they travel for some time, they are in suspension, then again they settle down, then again they jump over. So they keep on moving like a frog. So that is saltation, jumping. And the finer ones, that is the silt and the clay size, which the size you saw just now. So they are smaller in size, and they travel in suspension for a very long distance till they have the energy. They keep on traveling in suspension. Then some of the material also moves in solution. So this is another diagram to show the rolling and sliding of the bed load. And then you have the again this gravel, sand, silt and clay moving in along the floor of the bed to saltation to in suspension. So this is known as the suspended load, and this is known as the bed load. Again the same diagram just to show how the sediments move along the bed of the river and in suspension, as well as in dissolved. The one which is in solution, they are moving as dissolved load. Now this is a diagram to show that as you increase the energy, the size of the sediments that are transported keeps on moving. So for moving a clay size sediment or silt size sediment, you need lower energy, and for moving gravel, pebble, cobble and boulder, you need very heavy and lots of energy to move. Now this energy is gained because of the high gradient of the slopes along which the river is flowing. Similarly, if the energy reduces, then the heaviest ones like the boulders, etc., they settle down, they get deposited very heavy. Only a small drop in water velocity is needed to get them deposited. And for the finer ones, they are very light and requires almost quiet water. Like the clay will not get deposited until the water is very very quiet. So this is the relationship between the movement of the sediments to as well as how they settle down or get deposited. Now these two terms one has to keep in mind. They are the capacity and the competence of the river. The capacity of the river is to carry the maximum possible sediment load that a stream can transport. So a stream, how much capacity it has to carry the load. So if it has got some amount of discharge, how much sediments it can carry. So that is known as the capacity, and competence is the ability to carry the largest possible sediment the river will carry. So these are the two terms one has to remember. Then there is also a term graded stream. A graded stream is the one in which over a period of time slope and channel characters are so delicately adjusted as to provide with available discharge just the velocity required for the transportation of the load supplied from the drainage basin. That means whatever load is being supplied, it has just sufficient energy to carry them forward or to keep on transporting them. So we can say, in a way, graded stream is a stream which comes in equilibrium. We'll be discussing about it later on also. Now this is very important and we must understand. Now there's a term known as the settling velocity, or it is also known as the terminal velocity. Now what is terminal velocity? A particular size sediment moves at its terminal velocity if its speed is constant due to the restraining force exerted by the fluid through which it is moving. At this point, the object ceases to accelerate and continues falling at a constant speed, known as the terminal velocity. That means terminal velocity is the velocity of the stream for a particular size sediment to just keep it in motion, keep it moving. That means, suppose like you have a 10 millimeter or a 1 centimeter size sediment. Now it will keep on moving until its velocity is around, say, 0.70 meters per second. As and when the velocity of water becomes lower than 0.7 meters per second, this 1 centimeter or 10 millimeter size sediment will get deposited. It will not be able to keep moving, getting transported if the velocity becomes lower than 0.7 millimeter. Similarly, if the sediment size is say 10 centimeters or 100 millimeters, it needs a velocity of 2.5 meters per second to keep it in motion. Similarly, for the other sizes, like for 0.1 millimeter sediment, it needs a velocity of 0.0006 meters per second to keep in motion. So these are the smaller fine sand size sediments, and then you have got the silt size sediments. So that is important. Sediment will keep on moving or keep on getting transported until unless the velocity of water comes below its terminal velocity or below its settling velocity. So now again, this is the general scenario where the river begins from the higher in the mountainous region. Smaller tributaries, they join together, so initially the gradient is very high. However, the discharge is low. The discharge keeps on increasing as the number of tributaries they join together. Now at this point the river enters the plain. In this part, the river travels along a very narrow V-shaped valley. Here there is high vertical erosion. The river vertically cuts the valley. No lateral or very small, we can say insignificant lateral erosion or sideward erosion is there, because the rocks are all present here and it is not easy for the river to cut sidewards. It cuts vertically down, as we discussed in the last lecture. Now here what happens, this is the foothill. From here downwards you have the plains starting. So here the gradient suddenly reduces. Here it is very high, and here the gradient reduces, and then you have got the plains, and ultimately it is the mouth of the river and you enter into the sea, and this is the so there are number of landforms which are formed because of the sudden change in the velocity. Here the velocity is very high, so you have got erosional landforms, but here from this point onwards suddenly there is change in the reduction in the velocity. So whatever sediments which are moving here, as and when the velocity of water comes below their terminal velocity, they just start getting deposited. So the different type of landforms are alluvial fans, which are formed where the stream valley widens and it enters the plains. Then in the plain you have the floodplain deposits. We will be discussing natural levees, back swamp deposits, then point bar deposits, channel bars or the bed bars, and then delta at the mouth of the river. So like an example, I can tell you that the velocity of water is around 25 to 30 kilometers per hour in the upstream region of Haridwar, that means in the Himalayan region. The velocity is 8.3 meters per second. So as we had I had discussed, so for moving a sediment size of 10 centimeters, you need a velocity of 2.5 meters per second. So if the velocity is 8.3 meters per second, you can imagine that the river will be able to transport much larger sized boulders in the upper regions of the in the upper mountainous region in the Himalayan terrain. Now at the Haridwar, which is the foothills, the estimated velocity of water is at 10 meters depth is around 1.1 meters per second. So 1.1 meter is around this. So you can see that 20 centimeters or 20 millimeter, 22 centimeters or 20 millimeter size sediments, they are they get deposited as and when the river reaches Haridwar. So any of you, if you have been to Haridwar, you can see that you will find pebbles and cobbles all along the river bed in the region. Now, during the time of floods, the velocities reach to 4 meters per second, and they drop down to 1 meters per second when they during the time of the winters when the monsoons are not there. So this velocity, and depending on the change in the velocity, the size of the sediment being transported and deposited keeps on changing. So this is the alluvial fan which we were now coming down from the hills. It suddenly you enter into the plains, and suddenly the gradient changes. So earlier you are in this place in the higher, in the Himalayan region, the velocity is 8 meters per second, and the gradient is so high. And as you enter the foothill region, here the velocity comes to around 1 meters per second. So there is a drastic change in the velocity, reduction in the velocity, reduction in energy, and so the sediments will keep on getting deposited in the form of a fan. So this is known as alluvial fan. It resembles the table fan, wing of a table fan, you can see that. So this is known as alluvial fan because this material gets deposited all along this region. The size of this can vary from 100 to hundreds of kilometers that we'll be seeing. And beyond this point, you enter into the plains, the gradient suddenly comes down and you have more of deposition. So in this place, this is more of erosion. Here onwards, you have got extensive deposition. So you can see that in this alluvial fan region, you have got sediments right from say just take this pen as a scale. So this is around 4-5 centimeters in dimension, to smaller ones, to even coarse sand and gravel. Finer sediments will not get deposited here, they will be carried downstream with the moving water. So alluvial fans are flat to gently sloping masses of loose rock material, which is largely sand and gravel, that are shaped often like a fan. They form at the base of the mountains or in the foothills region that we have discussed, where the fast flowing streams meet relatively flat surfaces of basin floors or the broad valleys. At this juncture, the gradient of stream abruptly decreases, and boulders, pebbles, cobbles, gravel, sand, and other sediments are deposited. Now, this is another photograph, satellite picture, to show you the size of the fan. Now, these are the Himalayan regions. This is the famous Kosi mega fan downstream of Patna. This is the river Ganga, and this is the Kosi river, which is a tributary of Ganga. And here you can see that this is the channel which is shown here, and this is the active channel which is like this. And this, if you see that this is the boundary of this fan. So this is a large fan. Now if you this is the scale, so it is 60 kilometers. This bar is 60 kilometers. So this is around 250 kilometers in length and around less than something 200 kilometers in width. So that is the size of the fan. That is why it has been referred to as a mega fan in the of the Kosi river. Now again, this is satellite picture to show you. If you see, this is the hilly region upstream of Rishikesh. This is Devprayag. Here the river is flowing in a very narrow valley where you don't have lateral erosion, only vertical V-shaped valleys are present. Now as the river enters the foothill region, Rishikesh and Haridwar, you can see that there is more of lateral erosion, and the sideward erosion is there, and the river is now spreading. Now it is no more confined to those V-shaped valleys, and the fan formation is starting, and the sediments which are heavier in size, they start getting deposited. this is the river Ganga and other tributaries. This, if you look, this is Rishikesh. So this is the main river Ganga. It reaches Kanpur. So here we have got the Lucknow University Geology department, and these are the different tributaries. Yamuna here, and then you have got this is Ghagra. So this all the rivers, they keep on joining the river Ganga, and the important geometric features found in the plains are that now there is a widening of the river, and the floodplains start getting formed. Then you have got the meandering channels, Oxbow Lake, braided channels, river terraces, meander scars, paleo channels, that we'll be seeing just now. Now this is another diagram to show you that the river flowing in the mountainous region, it is confined within narrow valleys bordered by the rocks, so it is not able to erode laterally, but it erodes in a vertical manner, and so you have V-shaped valley. Now, as it enters the plain, here the widening starts taking place, and during the time of floods, the water flows in this region, and because the river is now not confined within the very narrow valley, it starts moving not in a straight course, but also it starts moving in a irregular manner, and this is much downstream. And here you can see that with the addition of a number of tributaries, the amount of water keeps on increasing, the discharge is high, and the floodplain formation is more intense, and you have wide and well developed floodplain formation, and hence the deposition of sediments starts taking place. So here from this place to this place, the gradient keeps on decreasing, and beyond this point the river meets the sea or the ocean. So this is the trunk stream or the main stream, and this stream now, it is not flowing in a straight pattern, rather it is flowing in a curved, the river starts attaining a curved nature. We had discussed in the while discussing the erosion that when this river will bend, the outer margin will have higher velocity and the inner will have lesser velocity. As a result, you have got erosion on this part and deposition taking place on this part. Now this is the main channel, and then these are the regions which are occupied during the time of floods. Normal course, the river will flow within the channel, but during the floods it starts occupying the floodplain, and because of this you have got the swampy regions in the away from the main channel. This is a Yazoo stream. Yazoo stream is a stream which flows parallel to the main stream, and it will meet somewhere downstream at some point. So for a long distance it keeps flowing parallel to the main valley. Now this diagram explains the formation of the wide floodplain and the formation of meandering channel. The river, when it adopts this curved path, it is said to meander. Now earlier this was flowing in a straight channel. During the floods you have got higher discharge, so lateral erosion is taking place, and the river leaves its straight course, it starts bending, and as and when it bends, the outer side will have more velocity, so it will keep on eroding this side as well as this side on the outer side, and sediments will start getting deposit on the inner side. So as the time passes, the lateral erosion continues, and the floodplain, it keeps on getting widened and widened. So here you have got a narrow valley, and here you have got broader valley. So upstream in the hilly region you have got narrow V-shaped valley. Here you have got a wide valley. So in this part there is very little of vertical erosion, but more of lateral erosion. Now what happens during the time of floods? The river leaves its channel and it overflows the banks. Now as and when it overflows the main channel, suddenly here the depth is reduced, and hence the energy reduces, and on the banks you have got deposition of coarser sediments, because here the velocity is higher and here the velocity suddenly reduces. So whatever sediments which are coarser, they start getting deposited on the margins. And when the floods settle down, when the river again starts flowing in this channel after the monsoons are over, so you will have these portions which are raised, and these are known as natural levees. So they get built up in subsequent years. This is again the diagram to show the natural levees. So they are the raised portion all along the channel of the river, and in this floodplain. Now when the floods are there, then the sediments, they get distributed in this part. So the coarser will settle near the river channel, and the finer will settle away from the main channel, and that forms the marshy land. So you have the swampy region, the back swamps, and when this river is meandering, then it forms Oxbow lakes, which we'll be discussing in subsequent slides. So here you have got a straight course. As due to little bending, there is more of erosion here, deposition here. Now this keeps on progressing, and finally what happens, a river has a very intense bending, and now what happens, that river has to consume a lot of energy. It has to reduce its velocity, it has to waste its energy while keep on moving along a bending channel. So what it does, it erodes this part, and when it erodes this part like this, so it is like this keeps on narrowing along the neck, and then finally this portion gets dislodged, and these are the past channels, and they get filled up with water. These are known as the Oxbow lakes. So you have got a number of Oxbow lakes, and this is the photograph which shows the aerial satellite data that shows the Oxbow lakes. That means the river must have been moving along this channel, but now it has abandoned and it has chosen a new channel. So this is the same how the Oxbow lakes are formed. Here you can see that earlier the river was flowing like this, but now it has straightened its course, and this is now left as an Oxbow lake. So again, so these as we discussed, that here there would be erosion, and here there is deposition of the sediments. These deposits, they are known as the point bar deposits. This is again the meander scars near Kanpur, upstream of Kanpur. The same photograph, the same Kanpur, and here they are the meander. So you can see that earlier this Ganga river had a large meandering channel, and now the channel has straightened down. Again the same meandering channels, and the paleo, these are the meander scars that are present, that shows that the river was flowing from this path, and this is Ghagra river, and it has changed its course. Then you have got another type of channel that is known as braided channel. Now, braided channels are interwoven network of channels separated by coarse alluvium deposits. They occur where sediment load is high and both discharge and velocity fluctuates rapidly. Now, what happens when the sediment load is high? Then during the time of high floods, they keep on getting transported. Now, as and when the floods recede, the river is not in a position to carry them forward and they get deposited within the channels. So these are known as channel bars. So these are sand deposits here, and the river water, it gets bisected and flows and then again joins. So such channels are known as braided channels. You can see them if you go to Kanpur or Allahabad. You can see them, a number of braid bars where even cultivation is going on. So this channel is from Kanpur region where the even agriculture is being done on these sand bodies. Now sometimes the braid bars during the next season they get washed away and a new braid bar would form. Finally the river reaches the sea, and there you have got the formation of delta. Now delta, the word is adopted out of the Latin word symbol delta, which is triangular. So it was the same as was the case of alluvial fans. There again the gradient suddenly decreased as the river entered the plains. Sorry. Now here again the river, when it enters relatively still water, the sea water, the energy is suddenly dropped down and the sediments start getting deposited. So this is you have got the formation of delta. So this is the initially it is like this, then this course of the river keeps on changing, and this is how the delta keeps on growing. The delta it has got distinctly three types of layers or beds. The ones which are at the base, they are bottom set. Then you have got the foreset which are inclined, and then you have got the again top set which are again horizontal beds. So you can see how these are formed, and this foreset, they follow the general profile of the sea floor, and then that is how they get inclined. And during the time of floods, the top set cover these foreset deposits. So this is these channels, they are known as the distributaries, and this is how the delta is formed. So ultimately the deposits, as I said, delta are in the form of cone. So you have got, like in the Ganga and Brahmaputra, they bring about a lot of sediments, and these sediments get deposited in this Bay of Bengal, and as a result the sediments which are brought by Ganga and Brahmaputra, they are carried almost 3,000 kilometers from their source, and then if we look below the water of the Indian Ocean, the sediments are deposited in the form of such a large deltaic deposits. So looking at the size and the shape, it has been referred to as Bengal fan, and it is estimated that almost 70% of the sediments which are brought are deposited in this Bengal fan have come all the way from the Himalayan region and brought by the rivers of the Ganga and the Brahmaputra basin. So it's a matter of energy, whether the river will erode, transport or deposit. It's a game of energy, and if the energy is low, the river deposits. However, due to some reason, if the energy increases, it will again start eroding its own deposits. The change of energy can either be due to change in discharge or the change in gradient. So that we have already discussed in the beginning, that whatever energy the river gains, it is because of the gradient in the high high up in the mountainous region, and then as the river comes down on the plains, a number of tributaries join and the discharge increases, so that also brings about the change in the energy. So uh, I think we'll take up something more about the geological work of uh, the rivers, and we'll be discussing some of the very important topics in our next lecture. Thank you.